Okay, howdy everyone. Continuing on our topic 10, motor skills. 10.2 is on a particular type of motor skill called tracking, stay on target, and then the concept of control loops as they can apply to how a human sensory motor system works. Okay, so again, tracking. This is the idea of a moving index where you are trying to hit a target or a moving target and either a moving index and a moving target, or one or the other is moving and the other is static, and you want to get those two to align. So you have an index that would be this circle here, the target would be there in the middle, and then there's usually some sort of noise or perturbation that makes this task challenging. So this is a screenshot of an interface or an environment that we use frequently in my research lab called the Multi-Attribute Task Battery 2, MATB2, developed by NASA. And it has a tracking task in it that we usually interface with a spring-loaded elastic joystick. And so, yeah, the joystick deviations affect the position of this index of this, thing that's being controlled, but there's also noise in there. So this thing is drifting around and you're constantly having to adjust, trying to get it on target. What makes this task interesting is it's continuous. And so if you saw in 10.1, right at the end, I talk about continuous tasks, one of them being driving a car. And so I'm continuously taking in sensory data, perceiving it, right? So I understand what that data means with regard to my task. And then I'm directly informing adjustments, to my tracking task in order to minimize the amount of error between my current index and the target. All right. So driving, if you think of driving, it's actually two concurrent tracking tasks. And so the way I like to put that, we are laterally tracking our position on the road. So I'm adjusting with my steering wheel controller where my lateral position is on the road. And I'm continuously adjusting that. So the road changes, it goes around a curve, or whatever. I adjust to that due to my sensory input. The second tracking task is I'm tracking longitudinally. So I'm adjusting my speed and I'm reducing speed and increasing speed based on a target longitudinal velocity. You might also say I'm using the throttle and brake pedals to change the position of this speedometer, right? So the index on the speedometer might be what I'm paying attention to. I know that this represents how fast I'm going, but maybe my goal here is to drive at or below the speed limit. This is also a tracking task, right? I'm trying to adjust a little bit in each direction, try to get it right on a certain target. All right, and we use, this is actually a screenshot of a driving sim that we use in my lab, where we may require people to really precisely drive at a certain speed and really precisely drive at a certain location on the road, and having those two tasks continually is a good way to keep a basic workload level. Okay. Now, factors that affect tracking performance, gain. And so maybe some of you have played with this before with like your mouse, the mouse, that you might use, or the trackpad that you might use to navigate, two-dimensionally for most, computer applications. We can adjust they call it sensitivity, at least in the Windows, so that a small amount of movement of my mouse results in a large amount of movement of the icon in the software, so the pointer, basically. And so I'm basically saying, for how much movement here is there movement on the screen, right, of my pointer there. So that's called control gain. The ideal is 1-to-1. So if I want my green arrow there to move, let's say, exactly 12 inches across the screen, then 1-to-1 mapping would be I move my arm with the mouse exactly 12 inches, okay? So if there's any multiple of that, there's there are costs, at least in terms of the human interaction. So ideal is one-to-one. That is the most clearly transparent in terms of how the humans will interact with it. The downside, of course, is when you've got maybe only, like this much mouse pad space, and you've got to cover, a larger space than that, in your virtual space. So you have to adapt, with those games, just to realize that moving away from one-to-one, there's going to be more error in these sorts of continuous tracking tasks. Okay, time delay and lag. This is something that means more to me in the last few years, as I've done a few projects that involve trying to get old school video games to work. I have a Raspberry Pi 4. I'm very proud of it. It has legal emulators on it and every game of my childhood on there. But because it's a little bit, well, it's not a polished system. It's designed to kind of work with open source stuff. There are aspects of it like the clock speed, let's say overclocking, that I'm learning about, and finding ways to reduce this lag between I press a button, I perform a control input, and that control input is realized in my, in the virtual setting. So we know about things, zero order, first order, second order systems from back in the controls topic, if you want to review that. But you remember a zero order system, the mouse is a zero order system because it's position based, right? So the input that I provide in this control changes the position of the affected system, right? Remember like if we had an old, a video game controller with a joystick, and I deviate this way to make the character spin in a circle. This is a first order controller because I'm controlling the velocity of that system. And then throttle and brake pedals in a car, or in a vehicle, those would be second order because you're controlling the acceleration of the system by the control input. So as those systems get higher and higher in order, the amount of delay that can be handled is more. Like, we can handle more delay, but that's really because the precision with trying to get exactly where you want to be, if you need precise like position control, you need less delay in your controller. If you are controlling something like the acceleration of a car, you've got a lot more kind of leeway to work with in terms of the time scale. So if you're trying to get I'm trying to drive right at 60 miles an hour, we have a little more leeway with the amount of delay that we can still effectively operate. But the more precise we need things, the smaller that the maximum acceptable lag would be. In general, one of the smart ways to get around this is to find ways to help the human operator recognize, yeah, there's gonna be some delay in the response of the system, but here is what you might expect to come here in the near future. So here's where you'll be in the near future based on your control input currently. Okay, so here's my Raspberry 4 example. So yeah, this would be an example of an old school game that I really wanted to be able to play again with my kids. I can successfully do it, but I've been able to test this and define, Raspberry Pi allows you to see like the input lag. So you press a button on your attached controller and then it'll tell you, yeah, 17 milliseconds or whatever. So what I was finding is I was having a really hard time coordinating. Like, I've played probably 1,000 hours of this game, the Super Mario Brothers. Probably before I was 8 years old, I played 1,000 hours of that. So I've got the motor memory there, and I'm ready to play again. But it's really hard. I'm not jumping at the right time. I'm running into guys. What's going on here? And so I look into the display lag, and I found out, well, based on my TV setting, I was running, and based on the control input through the Raspberry Pi, I was running about 100 milliseconds of control to display lag. And I'll tell you, that was enough to ruin the game for me. It was enough. It was too hard. Like I could tell, it was just enough behind, and I couldn't sync it up. I couldn't anticipate enough, to overcome it. So 100, according to me, unacceptable. Okay, so then I look into it a little bit more, and I find out, well, this is why we don't just use these cheap TVs. And I say cheap because I literally could have, for $500, I could be looking right now at a lecture slide that is probably, I don't know, 80 inches wide now. But the problem is, why don't we do that? If they're inexpensive, why do we buy these smaller $1,000, computer monitors? And a lot of times it's because of the update rate that the video can produce. So if you're using a larger display, it takes longer. The electronics, just aren't fast enough to get an instantaneous image. There's some image processing that happens, like between things. If you're watching TV, if there isn't a control input that you're really tracking, that you're really paying attention to, then it doesn't really matter. But if, you're trying to say, when I push this button, I want to see Mario jump immediately, I don't want to notice any sort of delay, you're going to have problems with that with a lot of standard TVs, unless you can change the settings to basically minimize the latency in display. So typical computer monitors are 5 milliseconds of delay. This is going to be better for precision gaming, let's say. So top gaming systems overall, between button press and display, they say less than 15 milliseconds is kind of where most really hardcore gamers would say they want their system. All right, so lag and latency, it's a problem in general, not just in serious things, like space operations, but also in video games. Okay, so tracking is an example of a continuous task, but we can also talk about the way that humans perform according to like control theory. So old school engineering control loops, where the human is part of this control, right? So there are aspects of the human in this. So this is in control loop. In control theory language, we have command input. Pressed a button, turned the steering wheel, deviated the joystick. There is an error between the target and the cursor, the two things I'm trying to line up. So I calculate that. I know what the error is here. The human operator then, processes that, determines what to do to overcome that error, applies that force to the control. The control applies its output to the system. The system responds to the control input, but also other environmental factors, the system responds. Okay, so if control input on this end, and then I just gotta wait until it comes out the other end, is the way that you would describe my my action. We'd call this an open loop activity, right? An open loop motor program. And open loop only to me makes sense because you contrast it with closed loop, okay? So a closed loop is whatever happens at the system end, I have an ability to immediately gain feedback about that, and I can incorporate that into my next iteration through this loop, okay? So whether or not that's there is the distinction between a closed loop system and an open loop system. Now, an open loop system, you may think, well, when do I ever do something and I can't observe the outcome immediately? Well, I would say, well, what if I change the thermostat? Okay, and if my outcome is, do I feel warmer or cooler? That's something that I'm not really going to get, at least not immediate feedback. And so I'm acting, it's not like I'm sitting there on the thermostat and adjusting and being like, am I warm enough now? No, more. I'm not doing this continuous adjusting of the thermostat. That doesn't really make sense because the feedback loop is effectively not there if I'm on this level. Yes, it does eventually get warmer, and then I'll know if I'm successful or not. But you got to think about these tasks like the speed in which the outcome of how you've acted on the system can be observed. Okay. So if we're talking about closed loop movements, these are literally, these are usually things very similar to what we were talking about with tracking tasks. So feedback is essential. It defines basically what you're doing. So I'm doing very precise tasks. So I'm doing dentistry. It's, every little movement I do, I am also taking in feedback of what I feel and what I see, and that's immediately directing how my very next millisecond of movement will go, right? So typically, yeah, precision sorts of movements. These are less sensitive to muscle state, like, am I fatigued? I've been dentisting all day. Yeah, I might be able to feel fatigue, but it's not going to, at least not as much as the alternative, affect how well I can do this task. Okay, I can be a good dentist all day, even into the 10th, 12th hour, right? In this motor sort of activity. Perturbations too. So, somebody bumps you or whatever, it's a little bit easier to regain control of that motor activity. Yep, typically we're using vision very heavily. Proprioception and kinesthesis, these describe the basically the internal sensation of the position and movement of our bodies. So when I close my eyes and I make a posture like this, I know where my hands are without looking at them because of proprioception. So the tension in each of my joints, the various haptic receptors there that are sending information to my brain. And as I movement is also giving, hey, this muscle is stretching and relaxing over time. That's also giving input, to my control center there. All right, so closed loop movements, being a dentist, being real careful with precision things. Now, open loop movements, these are again things where I'm going to execute the movement and I'm not able to really, on the time scale we're talking about here, I'm not really able to take feedback into account and adjust anything. So I've got a picture of a quarterback here about to throw a football. I call this an open loop movement, or a ballistic movement is another a term you may see here, because it's not like the quarterback can throw it and then as the ball is going, adjust anything about it. It's done, right? That ball is going according to the laws of physics, right? Even if you think about it this way, I'm starting to throw it, and here I may think, I need to adjust things a little bit. Let me crank my arm a little more like this. Let's get my fingers up. Like, these sorts of adjustments cannot happen on the time scale for the sorts of activities we're talking about here. A dentist could adjust his angle just a little bit, right? But a quarterback, it doesn't make sense to adjust the angle of throw midway through this motor activity. So these open loop ballistic movements, this is what I usually try to sort of make the analogy. It's like you load a video game cartridge in your head. Okay, this is my cartridge for throw a pass 20 yards down to that spot. I load it in, I press go, I execute it. Okay, I don't have a whole lot of time to tweak things. I'm basically throw it 20 yards. Okay, I have to throw it further. Well, I better grab the motor program for throw it 30 yards. I don't take the 20-yard one and adjust it. Okay, so again, this is kind of a little more like these are usually highly practiced activities if they're any good, and they're ones where the feedback you get comes from after the completion of the activity, and maybe makes you rethink, well, now I got to throw it a little harder next time. But that's not the same thing as adjusting my current throw. It's a different motor program. I'm grabbing the throw it harder motor program. Okay, so again, am I adjusting things as I go? Am I basically just, I hope it's a good throw because I've practiced so often that I know what a good throw should feel and look like. But I don't have time to evaluate and adjust anything at this point, right? So yes, higher degree of skill, highly sensitive to perturbations, unlike the closed loop movement, where if somebody bumps the dentist's arm, yeah, it might poke you a little bit, but it can recover pretty quickly. If this quarterback is trying to throw it and he is tackled as he does that, and his posture and his motion is all disrupted, that ball is not going anywhere near where he intended it. So it's very sensitive to perturbation, and also very sensitive to execution levels. So fatigue, at the end of a sporting event. Think like a pitcher in baseball or a bowler in cricket, where really precision is their game. And what happens as they go longer and longer, it gets wilder, it gets harder to control that sort of activity. Okay. Okay, so let's go through maybe a couple of examples. Now, normally I would invite open conversation to look at this scenario here and try to decide, is this open loop or a closed loop sort of activity? So let's talk about the little girl. This is my daughter, by the way, isn't she sweet? So this is me teaching her to ride a bike. So here she is riding a bike. Is riding a bike more of an open loop or a closed loop sort of activity? Now we might debate, well, to her or to an experienced bike rider? That's a good point. So for an experienced bike rider, though, I would assume, at least when I ride a bike, I am continuously updating my position in order to keep my balance. I'm continuously updating, where my arms are, how fast I'm pedaling, etc. So I would call that a closed loop activity because I'm continuously reacting to the changes in my environment, and that's guiding the control input. Okay. What about, let's assume this is obviously football, but this player wants to get through to get to the quarterback and give him a bad time, and this one does not want him to do that. So think about, for these two, is this open loop or closed loop? I would say to some extent, as they react to each other, it's a closed loop activity. However, if this guy wants to shoot past that guy, if he wants to, basically think ahead and, try to get around him, might be more of an open loop sort of activity because, hey, I'm going to shoot that gap there. I'm going for it. I'm not adjusting things as I go, really. Signatures. This one I feel very confident in saying this is an open loop activity. The reason I say it's open loop is, the counter argument here is, well, have you ever tried to do maybe just the first two letters of your name and then stop and then take a break and then go back and resume, or adjust things as you go? Oh, I should be a little bit smoother or whatever. You may notice there's not a whole lot you can do if you try to disrupt that loaded motor program of execute signature, right? So sign my name. There, that was it, right? What if I wanted to make the O a little bit larger or smaller or clearer? Sorry, because once I load that motor program, it's going to be what it is. And, there's a reason why people's signatures are so consistent and they can be, used for, analysis that way. It's because we don't really have room to adjust that motor program without completely disrupting the activity. If I'm playing tag, I'm chasing somebody, I may be continually reacting to their movements and trying to compensate. So you might call it closed loop, or you might say, I'm going to try to trick them and I'm going to try to cut them off at the pass. Maybe more of an open loop activity. So am I acting based on the feedback I'm gaining from the state of the system around me, or am I taking an action without really knowing exactly where I'm going to end up? I'm basically acting without waiting for input, on my surroundings to do that. Maybe this girl who's trying to run away, she's maybe more doing open loop sorts of activity, run this way, zigzag, serpentine, whatever. All right. Okay, so throwing a dart, doing these sorts of precision activities, I'm trying to hit the bullseye with a dart. I would say this is an open loop activity, just like throwing a football. So this guy, assuming he's a serious dart player, there's no adjustment of the motor program throw dart at bullseye. There's no adjustment as it's being performed. There might be load motor program, throw it at bullseye, and then I find out, oh, it's a little bit low, so maybe I then grab the motor program, throw it a little bit higher than bullseye. But there isn't anything, again, adjusting in my motion, in the action of throwing. This is a pretty open loop sort of activity. But again, maybe I see where the dart hits, or maybe I'm a pitcher and I see where the ball hits, and the feedback might be throw it a little bit higher, the motor program. So it's not, let me go back and do exactly what I just did, all of the exact same movements, but I'm going to adjust something a little bit this time. That doesn't work with the time scale of these sorts of activities. So you can get feedback, based on seeing where the ball goes or where the dart goes. But the way that you adjust to that is, again, it's just loading a different motor program. Okay, so it's still open loop. Each throw is an open loop activity, I propose. Even though when you see where it goes and you may adjust your strategy, you may adjust from there, what you're adjusting is which motor program do I execute, not how you execute that program. Okay. All right, that's it for the subtopic.